Okay, so I open SigMa once again, and now we will just go through each tab separately. Let me make the window a little bit bigger. Okay, so let's open again some NMR spectra. So let's open some urine NMR spectra. Okay, of course this is highlighted with red on purpose, meaning that please select your sample type. Urine. Okay, so if your data is acquired with an eretic signal, which is in this case is a known amount of the artificial electronic signal inserted, which corresponds to the certain concentration of the protons. So what you can do is you can try to normalize your data, or you can even try to normalize your data by TSP area. And we have included a box called normalized data box. And in this box, we offer you to use one of those 6 most commonly used normalization methods in metabolomics. So let's say we want to normalize our human urine NMR metabolomics data by the eretic signal area. So we go and say we want to use for that purpose a ref norm option, which actually normalizes by the reference peak area. And let's just start, okay, from which ppm. So let's say we start, because I know by heart, so this is positioned at ppm 12. So let's just say yes, 11.5 to 12.5, just to take it big. Apply. So what we have done now is we actually normalized entire our spectra by this area of the eretic signal. And how it has been done is also described in the paper, but briefly. So basically each spectrum, each variable of the spectrum is divided by the area of this peak, which is sum of this interval, is divided first, and we do it for all the spectra, and then we just, in order to get the scale back, we just multiply by the mean of the eretic signal. Okay, so after we have normalized, of course we need to accept this normalization, and when we accept, the button becomes green, and at the same time save button becomes deactivated, meaning that now you cannot save it. So if you want to save, you need to save while the operating button is orange. Yeah, now we will go to the next tab. It's called the reference alignment. In the reference alignment spectra, we have align reference signal. In the reference alignment tab, we have 2 steps of alignment. First is align reference signal. So what it does, so if you press just options, it offers you a range that you want to use this ppm range where you actually have your reference signal and you want to align entire spectrum according to this signal. So you basically want to align signal which is in this range, and rest of the part of the spectrum will be moved accordingly. So in this case, of course, it's TSP at 0 ppm, and let me just show you just by zooming. So right after you press alignment, this becomes orange again. You are welcome to zoom in and have a look what has happened to your reference signal. So you can see in the raw data your TSP is slightly misaligned, and here we have it completely aligned. So if we are happy, again right click, accept, and it becomes green. We also have included something called pre-aligned spectra, options of the pre-aligned spectra, and you can actually look at different regions here. So these regions are baseline to baseline separated regions which we included. So in this case we have included rather a large number of regions. This is because we know by experience when we run human urine proton NMR spectra, it's very complex, and sometimes we would like to align as a swift shift of this larger spectral region multiple times in order to acquire the optimal alignment. But you are welcome to just delete any of these regions you like, or you can actually add, delete, you can change their order. And this is max allowed shift in ppm, is how much each of this region you allow to be shifted either to the right or to the left. Okay, this we have included, we have to change it accordingly. Okay, let me just press. What happens? It takes some time to align all these regions separately. So in contrast to the reference alignment, when we do pre-alignment, we align each of the region separately, meaning that when we align one region, the alignment is done only inside the region. It doesn't impact the outside of that region, okay? So you can evaluate this, and if we are happy, we can just again press right click and accept this pre-alignment. And we continue to the next tab called interval recognition. This is probably the most important tab of using SigMa. So in this tab, what we have is we have all the mapping of the signature signals and signature signals of unknown spin systems are stored as a library, SigMa library of chemicals. So here you can see all of those. So this is basically the library. So we have the name of the human urine NMR metabolites and their chemical shift ranges. So if you don't want, for example, some of your signals to be included in the analysis, you can set this from 1 to 0, and they will not be included. And in these options, you can also select that you want to use, let's say, the automatic interval selection. And if you want, then you have to change this status from 0 to 1, and then you will actually use SigMa's automatic interval selection option, which will select all the intervals which is not included in this library. So it will only pick up the peaks if there is a peak, and this peak should not be included already by the user. So this is kind of an intelligent way of picking only those picks that are left out. So that will actually allow some unbiased pick picking. So if you press identify intervals, what we are doing is we are actually mapping the signatures. We are mapping the signature signals of the urine NMR spectra. Okay, in a minute we will see that we have mapped 125 intervals, and out of these 87 are the class 1, which is called in the paper SS, signature signals. And of course we can visualize them either by pressing show, and you can of course zoom in here. So we have 3 colors. So green ones are class 1 SS, and blues are class 2 SUS, and reds are class 3 beans. So you can zoom in, either you can zoom in and evaluate like this, or what we can do is we can also press evaluate intervals, and then we can try to say, okay, I want to have a look this. You can just choose to what to look at. and then you just plot, just as an example. So you will see that there will be three colors. So the gray ones is the one that is a row interval. This is a row interval of the histamine, and the black one is actually the reference human urine proton NMR spectra, which is included inside the SigMa. So this is a SigMa reference urine spectra, and what we have done is we basically mapped the histamine signature signal in that region using our reference spectrum. This is how it looks. So we have a row spectral interval, we have mapped one. So the purple one is actually corresponds to the gray ones, but it's just mapped, it's aligned towards our reference interval, towards our reference spectrum, sorry. Okay, so this is how methyl nicotinamide looks like, and this is how the mapped interval of histidine looks like: citrate, pyruvate, and acetate. So if you are happy with this mapping, then you are welcome to accept. If not, please go back to the options and redo it. You can also undo this mapping, change the options, and do it again. So here we also included something called the validation box. I'm not gonna do it now, but I just want to mention that you can actually, as in the data import data tab, you can actually import here also Bruker data or MATLAB data of your let's say authentic standards or spiked spectra in order to overlay them and make an ambiguous identification of your metabolites by comparing the chemical shift ranges of your real spectra with a reference spectra of your standards, for example. Okay, so let me just accept this and move on to the next tab. And next tab is called the interval alignment tab. So here there is not much options, you just press align. So what it does is actually those maps, mapped signature signals are now further aligned. So only the signature signals, only the class 1s are further aligned, and I will tell you why they are further aligned. Because all these class 1 signature signals, we quantify them using MCR, and we know that MCR works best and it's most reliable when the interval is aligned as much as possible. So just have a look at this one. So let's say this is pyruvate. You can see the alignment is not significant because during the mapping we already aligned them towards our reference spectrum. But sometimes spectra can be so complicated that when you map, the alignment may not be ideal because it actually iteratively aligns the given signature signal interval of each metabolite, only the class 1s. So if you are happy with that, go ahead, otherwise undo it and change in the interval recognition tab, change the interval ranges and so on. Okay, and I can also show this. You can press the show button and it will just show by again the 3 different colors. I will move SigMa slightly like this. You can see the 3 different colors here. This corresponds to 3 different classes: SUS, SS. You are done with interval recognition and you identified 125 intervals. You can of course zoom in, and let's say that you don't like some of the intervals and you want to make some changes. You want to change the ranges, for example. In order to do that, you will have to deselect all the tools from on this panel, and then you can perform this directly on the GUI here from the plot. And to do it, just right click and Then you can add new interval, or you can right click close by the peak that you want to change, and you'll have an option called change interval or delete the interval. So let's say here we want to change this signature signal number 21, and you can just drag the border of this peak just like this. Okay, and let's say that we also want to change peak 20. Okay, and let's say we want to delete 19, and let's say we want to add here one new one. And when you add, you need to give 3 inputs. You need to give a name. So let's say we give a name. We call it UN1, unknown one, and we give it to, let's say, class 2, which means unknown. Yes, do we want to include this? Yes, we want. And you can see it just inserts a row, a very narrow signature signal, and we can then press change, and make it the ppm range as we like to be, something like this. Okay, after you have done such manipulation, so we need to press identify interval button again. So let me just insert one more, so you will see that yes, so this time unknown 2. So you will see that we actually have now inserted one more interval, and when we map all the intervals, we should have 126 intervals. You can see here. Okay, so now we press identify intervals once again. You can see 126 intervals, and those that we have mapped are included. And to make it visualization better, we can just press hide, show, and then show it again. And you will see that we have now included those intervals.